Welcome back, everyone. We're going into our third season. It feels like a third session. I mean, it feels like a season. Thank you, everybody, for your patience. It's really my pleasure. I've been looking forward to hearing your talk, Eagle. Eagle is an aerospace engineer and wrote a book called Opening the High Frontier. And yes. Eagle is an aerospace engineer and has written a very exciting book called Opening the High Frontier, which is all about minimizing costs and making space accessible. And I really liked your approach. I wanted to say of not leaving any sort of older achievement unturned in the developments over, even from the 60s and 70s, some really prolific work. And it's always been fascinating, that kind of era where there's all these fantastic ideas where anything could be possible. And I'm just really looking forward to your talk. And thank you very much for joining us today. Ladies and gentlemen, Eagle, Sarmon.
Thank you. Well, I'm here to talk with you about what I call a combination launch system. This is something that will allow us to literally open up the high frontier for everybody. Make all of our dreams come true. At least that's my hope. I find it kind of interesting to review some of the past ideas. It all kind of started with Flash Gordon and Buck Rogers. I always liked that one. And then in the 50s, it started really getting serious. I don't know how many of you might be aware of it, but Wernher von Braun was the technical director for this. And this is actually the beginnings of a combination launch system. It has a ground accelerator. The rocket has some air-breathing propulsion on it. In any case, the dreams got even bigger and grander. There was going to the moon. Again, Wernher von Braun. Notice there's nothing shy about any of this. It's big, bold, and audacious. There's 3 ships, 10 men in each ship. The 200-foot diameter wheeled space station in it, which was, if memory serves, had about 1/3 of a G in it. And one of these ships, I think it's this one, was only for a one-way trip. It carried the tractors and the habitats for setting up the base on the moon. Here they are landing, and here are the tractors. You can see there's quite a few people on it. This is just no 2 guys walking around in the dirt. And then, of course, he wanted to go to Mars. In this case, it was a 10-ship fleet, total crew of 70, and again, cross-country trips across Mars. From there, the dreams have evolved. We're going to asteroid mining. I really like this one, space colonies. I'd love to get a job working on one of those. And then, of course, lunar cities. How many of you would take a job there if you had the opportunity? And then the biggest dream of all, terraforming Mars. And then, of course, for all of these dreams, you're going to need the spaceships for flying around the solar system. They're going to need crew. How many of you would go to a space academy for 4 years, get your astronaut ticket so you could crew on one? Yeah, that's what I thought. A few years ago, I went to the Maritime Academy and got my mate's ticket so I could sail ships around the world. Anyway, there's another one, probably a little more current, Nautilus X. And then the biggest dream of all, how many would like that one? In any case, besides being big, bold, and audacious and involving lots of people, what do all these dreams have in common? And that one item is affordable spaceflight. It is the foundation of every single one of them. There have been many ideas proposed for doing that. Space elevators, probably the best well-known one, but they're not buildable. The physics aren't there, for example, with the launch loop, or the materials aren't there for the space elevator. The combination launch system is based 100% on all existing technology. And as the name implies, it is a combination of systems. It can be air launch, something like the XS-1, and probably the least known, the non-rotating skyhook. It works by reducing the amount of velocity that the rocket-powered components need to achieve to get to orbit. This reduces the propellant fraction, increases the payload fraction, and in addition to allowing complete reusability. And it's by attacking the cost equation, the dollars per pound, both top and bottom, that makes it work. By the way, this picture is what it would look like from the bottom of a non-rotating skyhook in its mature form. There is actually gravity at the bottom of it, and this is what the view of the Earth would look like from there. In any case, the combination launch system, there are many ways to build it. It can start out with air-assisted launch, ground-assisted launch. The air-assisted launch can also be supersonic. This idea was from back in the 60s. It was to use the XB-70 to take a follow onto the X-15 up to Mach 3 before launching it. And then, of course, excuse me, this is a ground accelerator going up a mountain slope. This was proposed back in the 60s. Another way of making a ground accelerator is what I call a vertical accelerator launch tower. A couple years ago, there was a student I was mentoring, and she was really into rockets, and she wanted to build this. So we built a vertical accelerator launch tower, and this little rocket, it's just started its flight. When it clears the top of the tower, it's going a little over 100 miles an hour. And a fraction of a second after this picture was taken, the rocket motor ignites. There was an onboard ignition system. And it about doubled the altitude that the rocket would get. This could be expanded into a full-size system. In any case, since Stratolaunch is going to soon be flying, I'm going to be assuming that subsonic air launch is probably going to be the method of choice for the next few years. So the next step is, what do you carry on Stratolaunch? There are two choices. They're actually quite similar. One is the X-15, or an X-15 style vehicle. Obviously, the X-15 was quite small. Stratolaunch could carry a very much larger version of this. There's also DARPA and Boeing building the XS-1. This is another variation on the theme. It has a slightly higher design temperature, so it could get higher speeds. The X-15 was good for Mach 6, and it was 1,200 degrees, if memory serves. This is supposedly designed for 2,000 degrees, so that's going to be at least Mach 8. Now, one of the things that was proposed back in the 60s with the X-15 was adding what's called the Blue Scout rocket. This was a two-stage expendable. This is the first stage right here, the second stage right here, the payload there. And unfortunately, they didn't build it. But all the design and analysis was done, and it was capable of putting a 150-pound satellite into orbit. Now, this is what a combination launch system would do. It would start with a vehicle like the X-15 or the XS-1, and it would have a launch vehicle underneath that. Only in the case of the combination launch system, instead of using an expendable vehicle, we would like that expendable vehicle reusable. The first stage of that expendable could be made like one of the Maston upper stages, vertical landing coming down. The second stage of that expendable on the Blue Scout would be combined with a reusable upper stage. That reusable upper stage could be, for example, like Dream Chaser here, a horizontal lander, or a vertical lander like Dragon 2 here. The last component, and the least well-known one, is the non-rotating skyhook. This particular one is what I call a basic skyhook. This is the training wheels beginner's version of a skyhook. This one has an overall length of 200 kilometers. The lower end has an altitude above the Earth of 185 kilometers. The center of gravity, that's what's in orbit. The lower end is at less than orbital velocity for its altitude. So there is a certain amount of gravity experienced at the lower end. That's why it's hanging on the rope or the cable. The space station has shifted above the center of gravity. It's counterbalancing the weight of the cable in the lower station. Anyway, there's some numbers there for it. It starts out in a baseline elliptical orbit, in this case, for this example, 350 kilometers by 445. Docking occurs when the skyhook is at the low point of its orbit. And when that happens, it shifts the center of gravity of the skyhook down. And this pulls it into a lower orbit, in this case, a 335 kilometer circular orbit. Now this is the approach configuration. Here's another picture of it, looking down the cable. Here's the central station moving down the cable towards the lower endpoint station. And this gives a little more detail of what a midpoint station might look like. It's basically based on space station, International Space Station technology, plus a inflatable module from Bigelow. This is a airlock module here. There is a porch there on it. There's another one facing the other way, and we'll get into that in a little bit more. And this is a view, again, looking down the cable at a Orion spacecraft on a suborbital approach path, approaching the bottom end of the station. Now, in this particular case, this 200-kilometer long skyhook, the lower end point is reducing the velocity, has a reduced velocity of orbit there of about 260 meters per second. So it's reducing the velocity that the spacecraft has to achieve by that much. This allows it to carry a larger payload. Here's another view of the approach. Basically, it works with a differential GPS system on both vehicles that are communicating. It just has to get within range of the crane arm on the lower end, where it then gets grabbed on. And there it is docked in position. Hopefully I'm speaking loud enough so you can see this. This is the approach configuration. Where my hand is the center of gravity. That's the part that the orbital altitude is. In the beginning, it's at 350 kilometers. The bottom end is at 185. So the approaching spacecraft is coming up on the suborbital path, and at the top of its arc, altitude and velocities match. They have a couple of minutes there for the crane on to grab it and hook on. At this point, once it's hooked on, the people can move out of the capsule into the lower endpoint station where they have a little more room, a little more comfort. This midpoint station here starts sliding down the cable. Now, since it's much more massive Then the cable does the majority of moving, but the Central Space Station does move down in altitude. Again, it's the center of gravity is what's in orbit. It's now, with this additional spacecraft on it, in a 335-kilometer circular orbit. So this weight down here is counterbalancing that up there. At this point, the midpoint station and the lower endpoint station are docked together. And that's the next part. Here it is. The station has gone down, as I just showed you, and it is now hooked up right there with the lower endpoint station, and that is the docking tunnel to allow people to go from one to the other. At this point, crew change is possible. The people coming up, the cargo coming up, they all go into the midpoint station. The people going home get into the spacecraft. Garbage going home goes into the spacecraft. Returning spaceflight experiments go back. Okay, I'm getting ahead of myself here. At this point, for them to go home, we do the same thing in reverse. The center of gravity is about here. They've done the exchange. It starts going down. And it gets to about here, which is where we started at. This is what's in orbit. The bottom end is now back at 185 kilometers altitude. It is moving at less than orbital velocity at that point. The moment the spacecraft drops off, it is falling back to the Earth. There is no re-entry burn required. So you have to wait until the skyhook is in the correct position for the release so that your returning spacecraft lands where you want it to. And that is how the basic crew change operation works. It saves 260 meters per second on this particular skyhook. It pulls it down into a lower orbit. When it drops off, the center of gravity drops back down, and it's now in a higher orbit. Oh, excuse me, it goes up. Anyway, we're now back in the original orbit, 350 by 445. So you're reusing that orbital energy, the difference between the 335 and the 350 by 445 orbit is being used to lift the spacecraft up, and then it's then given back to the skyhook when the spacecraft leaves. It's this reuse of energy that what makes this Earth really work. Now again, this is a beginner. This is like a 5-year-old's bicycle this big with training wheels. This one has not been built before. I figure that's the best way to start. The nice thing about this cable material, it's graphite thermoplastic. You can add to it in space, so it can be lengthened over time. And that is what you would do with it. As flights go up, as the number of flights increases, you're making money, you take extra cable material up, and you add it to it so that the cable gradually gets longer. Now there is one other very significant use for this besides just bringing things up from the Earth. The upper end of the cable is going at faster than orbital velocity for its altitude. And you can use that to launch spacecraft to higher orbit without using any of the spacecraft's onboard propellant. So in this case, the spacecraft, instead of being returned to Earth, I'll just go back to the model here. Okay, the arriving spacecraft is at the bottom. The midpoint station has come down to meet it. The instead of returning the spacecraft down, they transfer it onto the midpoint station. At this point, you do this, and now you transfer the spacecraft and any people on it, it could be a satellite, it doesn't have to be manned, to the upper endpoint station. Once they're on that, you do this again. And now, that is up there, this is here, and that is moving faster than its orbital velocity for its altitude. So when it drops off, it's getting a free velocity boost. When it does that, it drops the skyhook into a lower orbit. So there's one intermediate step in there. Before you take it all the way up and do the release, when you get to the middle here, now the spacecraft is here. This has an ion propulsion system on it. It uses that ion propulsion system, an ISP of about 3,000 seconds, so it uses very little propellant. And it gradually raises its orbital altitude. The higher you raise it, the more of a kick you're going to get at the upper end. So when you get to, and again, we're starting now from that circular orbit part. So you're spiraling out, and you get to where you want to go, you push it up here, you do the release, and now this drops into an inscribed elliptical orbit. You need to do that. You need to do that, otherwise you'd be dropping it into the atmosphere. So there's no free lunch, but it gives you a lot more efficiency. It's a way of using an ion propulsion system for an upper stage where you're not throwing it away. You keep it on the station, you reuse it over and over, and the propellant needed for it gets brought up by the arriving spacecraft. There's the ion propulsion system, and there is the space station, or the spacecraft being released from the upper end. To give you an idea on the actual performance of the system, the X-15 with Blue Scout rocket, as I told you earlier, had a payload capacity by itself of 150 pounds to orbit. Now, if you update that X-15 with a LOX methane rocket motor, which is a higher ISP, and add the 200-kilometer long non-rotating skyhook, the payload to the skyhook goes up from 150 to 605 pounds. You increase the length of the skyhook to 400 kilometers, and the payload goes up to 840 pounds. So substantial increases here. Give you another idea. This is the Titan Gemini launch vehicle. Its gross payload to orbit was 3,600 kilograms. I'm assuming that if you made that into a delivery craft for a space station, it would have a payload capacity, useful payload capacity of about 1,260 kilograms. If you launch that with a 600 mile per hour vertical ground accelerator or a mountainside ground accelerator and went to the bottom of the 200 kilometer long basic skyhook, that payload capacity goes up to 3,850 kilograms, 3 times as much. So you just cut your cost to getting to orbit to 1/3 of what it was without the ground accelerator and skyhook. Now this is an example of what I call a mature skyhook. This one has an overall length of 2,200 kilometers. The lower endpoint velocity is 80% of circular orbit velocity for that altitude. That's a velocity saving of, 1,560 meters per second. The upper endpoint velocity is 91% of escape velocity for that altitude. So that's almost a free return orbit to the moon. Total mass of this system, about 850,000 kilograms. The majority of that is in the cable. As the cable gets longer, it becomes a much more significant component. Again, the lower end point is 185 kilometers up. And when you add in complete reusability of the system and the increased payload fraction, the estimated cost is under $100 a pound. And this includes amortization of the investment, interest on the investment, profit, all maintenance costs, all recurring costs. A totally mature vehicle would be probably quite a bit different. One possibility would be to air launch something like this that could fly directly to the bottom of the lower end of the skyhook. This particular design was, what was his name? Hold on. It's from back in the 50s here. Well, if anybody's interested, ask me. I'm not going to take line looking for it here, but I thought it was a fun design, and it is quite workable. This is another spacecraft that has what I call a TRCC propulsion system, which is turbo rocket combined cycle. That means it has afterburning turbines, ducted rockets, ramjets, and scramjets, all in a shared flow path. And it's designed to fly directly to the bottom of a skyhook without the carrier aircraft. It could also be weighed in at about 380,000 pounds gross takeoff weight, and would carry about 40,000 pounds to the bottom of the skyhook. You could simplify this vehicle by taking the turbines out and air launching it with stratolaunch. Again, price is well under $100 a pound to orbit. Think about that one for a minute. If a seat weight per person is 200 pounds at $100 a pound to the bottom of the skyhook, $20,000 for a ticket. How many of you would buy a ticket for $20,000 to go there? Yeah. Hey, who do I give my money to, please? To me, I think that will transform the way we do business in space. It makes everything, the starships, the moon bases, the space colonies, all become possible. The key to it is that none of these ideas by themselves will do it alone. I've spent a lot of time analyzing all of them. Reusability, as is being done by SpaceX, is great. You know, they're talking about a 35% price reduction right now. As they get going, they might get down to a 50 or 60% reduction. But that's, right now, the Falcon 9 has a gross takeoff weight of 1.2 million pounds. It delivers 6,000 pounds of useful payload to the International Space Station. That's a payload fraction of 0.5%. It's $60 million per flight. That's $10,000 a pound. That's what we have now. That's the significance of the combination launch system. You can only go so far by reducing costs with reusability. To go further than that, you're going to have to attack the amount of useful payload that it carries. And that is what the combination launch system does. When you do that, that's when you can get to the $100 a pound. In any case, progress to date. Obviously, Vulcan Inc. is building Stratolaunch. Boeing is building the XS-1. Masten Space Systems, SpaceX, and Blue Origin are building vertical landing rockets. SpaceX and SNC, Sierra Nevada Corporation, are building reusable spacecraft. And Bigelow Aerospace is building inflatable space stations. All that's missing is the non-rotating skyhook and the vision to combine them all together. We are that close. So what are we waiting for? I want that Starship. Anyway, if you want more information, these are some search terms you can put in. I've been putting a lot of stuff on the internet on it. Any questions? Well, thank you. Isn't this working? Oh, okay. Okay, good. You pick them, whoever's closest. How about that gentleman right over there?
You compared your system to yet be built with systems that are flying right now, Falcon. If you compare it with the interplanetary transportation system, which similar to yours isn't flying now but is in development, the Earth to LEO is $70 a kilogram for the ITS. That's projected, obviously, which is within the error bars. It's the same as your number, really.
Cost analysis. There are a huge number of opinions on that. A lot of people who I have met in the aerospace business usually only show recurring costs. There's a big difference between just showing recurring costs and amortization of investment, profit, and all of that. I don't see how they can get costs like that with that system when you add in all those factors. I'm sorry. I think they're using a different cost modeling technique, and so we're not, the end result is you have an apples to oranges comparison. I've heard SpaceX say that their reusability was going to get it down to pennies on the pound, or pennies on the dollar, excuse me. And yet when they finally got their reusable first stage flying and came up with prices to it, it turned out to be a 30% price reduction. So there's a certain element of exaggeration, I think, that goes on. But also I think it's a lot of times people are talking just recurring costs and not total cost. I hope I've answered your question.
Well, I'd just like to point out that they're building and flying spacecraft, and the first companies dropped the price in 30 years. Gotta give them some credit.
I am in no way, shape, or form trying to take away any credit. Reusability is a key part of this. Again, there's no one single component by itself that will do it. With reusability, you still, even if you get it down to the spacecraft costs almost nothing, you still have insurance, you still have amortization, you still have maintenance, you still have profit, you still have range costs, you have refurbishment costs. I don't think it's possible to get a 90% reduction, but even if you do, at $10,000 a pound, that only gets you down to $1,000 a pound. The only way you can get the price lower is to increase the payload fraction. And that's what this is about.
Current price on Falcon Heavy is $1,400 a kilogram. So start there.
Okay. What is the last time I looked at the SpaceX site, they did not have numbers up for the Falcon Heavy, but it's been a few months. So I'd have to take a look at that. Okay, great. Now, whatever their price is, if they put it on a 600-mile-an-hour ground accelerator and flew it to a 200-kilometer-long non-rotating skyhook, they would triple their payload capacity and they would cut their cost to 1/3 of whatever it is today. That's the impact. This works for any launch vehicle. Have I answered your question, sir? Thank you. Anybody else? Yes.
Earlier, did I understand you to say that if you released a vehicle from an altitude of 185 kilometers, there would be no reentry, heating, significant reentry heating or reentry dynamics?
No, there would be no need for a retro rocket burn. It's moving at less than orbital velocity when it's on the hook there. So it immediately goes into a reentry orbit. The spacecraft immediately drops into a reentry orbit, and it still gets hot. But since it's not going as fast, can you hear me? Can- How's this? Okay. When it drops off, it drops into a reentry flight path. It still gets hot. It still needs a heat shield. But since it's not good, as the cable gets longer, when the cable is getting to the point that the lower end is only going at 70 or 80% of orbital velocity, the amount of reentry hitting is significantly less.
It's just less. Okay.
Mm-hmm. Yes?
Here.
Based on what SpaceX's $90 million launch for Falcon Heavy, the 16,800 kilogram payload is about $5,400 a kilo. Just for everyone's clarity, that one was just close to the engineering standard. It's not $1,400.
Okay.
Falcon Heavy,
Falcon Heavy, $90 million for Falcon Heavy launch.
And you got to at least launch a substantial satellite. It's not going to be very easy.
it's 53 tons.
16,800 kilos. She put it.
Leo.
Thank you.
Hi.
Sure.
Still working? Good. I certainly will love this if it all works, but I have a few concerns. First of all, and maybe this is just a question. I don't remember from the first slide, but you have to launch to get that cable or ribbon up there, and it was hundreds of thousands of pounds or kilograms, right?
The original, okay, let's just go back
Okay.
there.
Secondly, the question is, have you addressed dynamics or undulations that might damage the cable? And thirdly is collisions with space junk.
Okay, there's a number of questions there. The lower endpoint station will have thrusters on it, side to side, fore and aft. So you can use that to help damp out dynamics. If when the approaching spacecraft, when it gets to the bottom, when it's grabbed, if it still has forward velocity or is a little bit slow, any difference in velocity, it will put a little bit of a swing into the cable. So you can either dampen that out with the thrusters on the arriving spacecraft, you can dampen it out with the thrusters on the lower endpoint station, or you can just let it swing and it'll dampen out on its own because it is gravity gradient stabilized. Remember, this part is not in 0G. It is hanging on the cable, so there is weight there. So it's kind of like, think of it as like a rope. You built a tree house when you were a kid? Who built a tree house when they were a kid here? Anybody? Good. How long did it take you to figure out to hang a rope down to start pulling things up? You used a rope at all, or did you carry everything up on your back? My friend and I, we used a rope. That's what a skyhook is. It's the rope hanging down from the tree house to pull things up. Yes, it'll swing, but you can dampen them out. The micrometeorite problem, yes, it'll occur. The cable is designed with a safety factor of 5 to 1. Am I coming through clearly? Okay. In the 200-kilometer long skyhook, let's see, did I put the weight of the cable in here?
Yeah, 150,000 kilograms.
Oh, that's the total mass of the system. My memory is that the cable weight in this case is only about 15,000 kilograms. The cable only weighs about 10% of the weight for this length. So it's a very minor weight. The space station and the ion propulsion system are the majority of it. In any case, because it is graphite thermoplastic, the idea was to have a couple of heated platens up on at the midpoint station. So every time the station goes up and down the cable, it will have sensors inspecting the cable. When it sees a hole, it can put a little sheet of graphite thermoplastic on it, squeeze it in with the platens, heat it up enough to melt it in, and then it keeps right on going. It's a good example is the Golden Gate Bridge. The cables for the Golden Gate Bridge, every year, they paint it again. They start at one end, they sandblast it down to bare metal, they primer it, they paint it, they go from one end to the other. And when they get to the other end, they go back and start over. There's going to be ongoing maintenance on this, pure and simple.
Yeah, at baseline orbit of 350 kilometers, there's still quite a bit of atmosphere. Will there be, have you considered the drag and voltage potential between
There will be a
The-
small
the-
amount of drag
that
in the
and the
system,
approaching spacecraft?
but that is what the ion propulsion system will also make up. Yes, sir.
Yeah, where is the drive mechanism and how much does that weigh? Where's the drive mechanism for the system
Okay.
along the chain?
It's on the midpoint station here. One of the pictures has it. There it is. This is the backside view of the midpoint station. There's the inflatable module there, cooling vanes, solar arrays. Here's the lower endpoint station hooked up to it here. And then those are the thrusters. Yes?
A question and a comment. When you talk about an assisted ground launch, are you talking about like an electromagnetic railgun system?
It could be that. Are you familiar with rocket sleds?
Yes?
Basically, it's
Yeah.
steel rail, train rail.
Okay.
They're welded together into a continuous length. They put tension on them so that even when they're out in the desert, no matter how hot it gets, they're under more tension than the heat. So they don't warp. And they don't use wheels. They use what are called slippers. They just slide on it. If you look at some of the pictures of them when they've done them, you'll see the trail of sparks from the slippers going down the rails. They have gotten speeds of over 6,000 miles an hour on those.
Okay.
The Navy has, just in the last year, tested a 600 mile an hour maglev system. Either one would work. You could put them on a mountain slope. I think the higher up you put them, you can go to a higher top end speed. The limiting speed is the max Q of the vehicle. There are certain advantages there's advantages and disadvantages to whether you use ground-assisted launch or air-assisted launch. There's room for both.
Okay.
And which one will be the most cost-effective over the long haul, I haven't a clue.
Okay. My comment would be, my concern, bringing a bunch of new technologies together relative, almost at the same time, I would be concerned about what corporate risk aversion, but especially governmental risk aversion to bringing, the inflatable, the carbon fiber, refurbished X-15s, putting this whole package together. Could take decades.
Well, this is why I kind of like the way things are going now. I love what NASA has done. I am very clear that because it's public money and taxpayers get incredibly upset when there is an accident, that they have to be very risk averse. Reminds me of a quote by Wernher von Braun. When you're doing research, you're doing what you don't know what you're doing. There will be mistakes. You look at the development of aviation. A lot of test pilots have lost their lives pushing the limits. One pilot was lost flying an X-15 at about 4,000 miles an hour. Good Lord, I mean, the space shuttle, we lost 2 complete crews. It goes with it. The problem of NASA having to be so risk adverse really kind of ties its hands and drives the cost and the time frames way up. I think, so for them, this might be uncomfortable to work with. Ground accelerators have been around since the 40s. I mean, well, Christ, they've been around since 1903. The Wright brothers' first airplane was launched on a ground accelerator on the sand. V2s, or V1s, excuse me. I have heard one story that one V2 was launched on a ground accelerator to extend its range, but I've never been able to get confirmation on that one. They've been around a long time. They work, they're simple, they're cheap. Air launching has been around for a very long time. I mean, look at all the rocket planes from the 40s and 50s, and then there was the X-15. The D-21 drone was supersonic air launched on the SR-71. They did it 4 times. The first 3 were successful. They changed their procedure a little bit on the 4th one, and they lost both vehicles. There is risk. You're not, you know, when you're starting with anything new, you're not going to get rid of it. Graphite fibers have been being used on airplanes, God, since the 60s. I was working with graphite thermoplastics for the F-22 back in late 80s. These are not new technologies. The inflatable space station that's used here, it's not necessary. It could be a can, just like one of the ones used on the International Space Station. So really, the only thing new here is combining them all together. Yep. But again, it could be done incrementally. I know there's